welcome back. In the last class, we had seen the basics of how to design a neural network. Let us continue the session, and we will be seeing the most important concept, and this is the last concept. Then we will be moving towards the hands-on using Google Colab. So here we are discussing the optimizers. The different optimizers that we can see here are, these are 7. Along with that, there are a few more optimizers. We will see that going forward. What is the role of this optimizer? The main aim of this optimizer is to reduce the loss value, whatever the loss that we are going to get by comparing the predicted value with the ground truth. So our aim is to reduce this loss. So how is that we can reduce the loss is by updating the weights which are there on these connections. So we have to update the weights on these connections. Okay. Now, who will help us in updating these weights? It is these optimizers. So these are the different optimizers, and where is that you will be writing this code? I think we have seen during the loss, when we are calculating the loss in the compile function, we are passing the loss, what kind of loss, and then what is the metric that we are using. There only we have to use even optimizer also. What is the first optimizer that we are seeing? The most commonly used optimizer in a neural network is ADAM, adaptive moment estimation. So this is the most used optimizer. Yeah. So the different, we have many such different optimizers based on, once again, your problem statement. There is no specific optimizer works well. So you have to keep trying. Therefore, this is again an hyperparameter. So now, we have ADAM. Now you can even customize this optimizer. If you are customizing this optimizer, you can fix a different learning rate, how quick you want the convergence, how quick you want your model to learn the weights. So we can use an learning rate. You can change this learning rate because there is an this an hyperparameter. So if at all if you are changing the learning rate, you will use can you see the difference between this and this? So you can you can import this ADAM, and then you can call this particular optimizer. The second optimizer what we have is a stochastic gradient descent, and we have stochastic gradient descent with momentum. So if you are using SGD, then the optimizer is SGD and then the learning rate that you are defining here. With the momentum is just an hyperparameter. Therefore, you see along with the learning rate you are also writing the momentum. If you are writing the momentum, then the optimizer that you are using here is a stochastic gradient descent with the momentum. If you are not specifying the momentum, then the optimizer that we are using here is a stochastic gradient descent. Why is that it is so important? So once you use this, if you are using for any to solve any of the real time project, so there you need to be very clear what optimizer that you have used, so that when you are documenting, it will help you to say that we had used the optimizer stochastic gradient descent with the momentum. So if you are using a momentum, then it is SGD plus momentum. So it is very important for you to know what optimizers. Then we have the next optimizer that we have is RMS, root mean square propagation, RMS prop. This is the another variant of an optimizer. In case if you want to use this optimizer, then import this optimizer and then change this place. Rest everything, you see, I am not changing the loss value and then the metric. Let us assume we are solving a binary classification. Because it is a binary classification, the loss function is binary cross entropy and the metric here used is accuracy. But what is constantly we are changing? If at all if you are changing an optimizer, different optimizers, so the in the code you are going to change only this is the place where you are going to change it. Next, ADAGRAD is one more variant. If you are using import ADAGRAD and for an optimizer pass ADAGRAD. ADA delta is the next optimizer. So import ADA delta and optimizer you use this. Then we have an Adamax, which is an variant of Adam. So import Adamax, and this is the optimizer. So this is one more variant, and if you are using it, this is how you are going to do this. So these are the different optimizers. Along with this, we also have gradient descent. Then we have mini batch stochastic gradient, mini batch gradient descent, and then we have a stochastic gradient descent. So along with those 7 optimizers that we have seen, we have 3 more. Which you know, gradient descent, stochastic gradient descent, and mini batch gradient descent. I think stochastic we have seen in the previous slide. Now what makes a difference is when we are dealing, when the optimizer you want to use is mini batch gradient descent, the change here is during the training time, the batch size that you are going to specify. Look at the batch size, look at the part of the code which is being highlighted here, look at this. Now if you are using a gradient descent as an optimizer, so what will be the during the training, you are passing the entire training set for learning. So the length of your training x underscore train, length of your training data set is your batch size. If at all, if this is your batch size, then the optimizer that we have used is, although the word stochastic gradient descent, because the batch size is length of your training data, the optimizer is gradient descent. Next, mini batch. What is the word mini? Mini is a small. You are not passing the entire data set for learning, you are passing a part of it. When you are passing a part of it, definitely you will not pass the length, you will pass some number. That some number here is 32. Is 32 is fixed? Definitely no. It is once again an hyperparameter. You can keep changing this number and see how the performance is varying. Then what is stochastic gradient descent, SGD? You see the batch size is 1. So in case if you want to understand how we are going to do this, now you are going to get the loss value. Now if the loss is calculated by considering only one sample is being passed, then you got the prediction for that particular sample, and then you are comparing that prediction with the ground truth. Then based on the loss, you are coming back and then you are updating the weights. After every sample or after every instance in the training data set, if you are calculating the loss, then we call it as a stochastic gradient descent after every sample. Therefore, because the batch size is 1. No, I do not want to calculate after every sample. Let me pass I have passed the first sample, first instance, I have got 1 loss. I have passed second instance, I have got the loss. I have passed the third instance, like that I have passed 32 instances. After passing 32 samples, I am then calculating, we are calculating the loss after every sample, but weight updation is done after passing the 32 samples. I hope you are getting a difference. When you are passing a stochastic gradient, after every sample you are calculating the loss, you are coming back and you are updating the weights. Rather than doing it after every sample, in mini batch what I do, we pass 32 samples. 32 samples have been used for training. Passing here is passing through a neural network, and then you are getting a loss for every sample you are getting a loss, but weight updation is done after getting all these 32 values prediction. You will add up all these losses and then you will come back and then you will update the weight. This is one way of doing it. What happens in a gradient descent is, I do not want to do it after every, I do not want to do it after a few samples. I want to pass all the training samples. After passing all the training samples, I will calculate the loss and then I will come back and update. So here in this, the weight updation for every epoch will be 1, because after you are passing the entire training samples, and then you are calculating the loss, and then you are updating the weights. So, this is what is the different optimizers. Once again, optimizers are hyperparameters. You can use different optimizers based on the problem statement that you have taken. And the last line during when you are writing a code is you have to train your model. How is that you will train the model? By using a function called fit. Fit is a function which is used for training. Now, for training, what is that we will pass? If it is an classification, if it is a supervised machine learning data set, if it is a supervised data set, you will pass both features as well as the labels. So, you will pass X train as well as Y train as the parameters to this model fit. And how many epochs that you want to run for this? We want to run this entire for 100 epochs. So, this is what is this is how you will be designing the neural network. So, before we actually get into the hands on, let us quickly summarize what we have seen, and then we will open an Google Colab to run this. So, what we are solving? We are learning a multi-layer perceptron, which is ANN. Okay. Now, this is using this, what all two problems you can solve? You can solve a regression problem, or you can solve a classification problem. Now, what exactly is a regression problem? Regression problem is one where you are predicting a number. You are predicting a number here. Whereas here already there are predefined classes. To one of the class you are going to put your instance. Next, again under classification you have two types. What are those? You have a binary classification and we have a multi-class classification. Multi-class classification. Okay. Next, when you talk about a neural networks, so we have an input, we have an output, and we have an hidden layer. Hidden layer. Now, when we talk, we usually do not call it as an input layer. Let us call it as an input, hidden layer, and output layer. Let us talk about output. When it is a regression problem, number of neurons at an output layer will be 1. And what is the activation function that we use? The activation function that we use here is linear activation function. And next, what is the loss function that we use when we are solving a regression problem? It can be a mean square error, mean absolute error, root mean square error, and so on so forth. What is the metric that you will be using along with calculating the loss? It can be any one of this metric. So, this is all with respect to the regression problem. Now, let us see when we are solving a classification problem. So, for a classification, when we are dealing with the binary classification, how many number of neurons that you place at an output layer? We will place 1 neuron. What is the activation function we use at an output layer? We use a sigmoid activation function. Then, what is the loss function we use when we are dealing with the binary classification? We will use a binary cross entropy loss function. And what is the metric that we use when we are solving a binary classification? It is an accuracy. Next, multi-class. How many neurons that you put at an output layer? That depends on number of classes. If number of classes are 3, we will place 3 neurons. What activation function we will use? We will use a softmax activation function at an output layer. And what is the loss function that we use? The loss function will be either categorical or we will use a sparse. So, that depends on how you are doing the label encoding, whether we are using label encoding or we are using one hot encoding. How is that? In the pre-processing you will be deciding this. So, this is very important before you look into an before you start doing a project or before you start working on a real time project. Yeah, this is just by looking at your data, this is all the information that you need to know it. Now, coming to an hidden layer, there is no restriction on a number of neurons that we are going to. Let us erase this part. We do not have a restriction on number of neurons that you place at an hidden layer. So, let us see this. Now, you can have any number of neurons, we can have any number of layers. Now, so what is the only thing that you should know? What is the activation function that we can use at an hidden layer? At an hidden layer we can use an ReLU. ReLU is most commonly used activation function. Otherwise, other than ReLU we have leaky ReLU, we have parametric ReLU, but you know, the most commonly used activation function here is ReLU. Then what else we have discussed? Now, once we get a loss, when we are back propagating, our main aim is to reduce the loss function by modifying the weights. So, therefore, we have an optimizers that will help us to do this. There are different optimizers. The most commonly used optimizer is ADAM. This is most commonly used optimizer, but not necessarily that by using ADAM you should get a good performance based on your problem statement, based on the type of the data set that you are using. You can change the optimizer and then see which optimizer is giving you the best performance. Once you complete this conventional way of doing, then the next what you can do is you can try adding the dropout. What is a dropout? Dropout is one which will skip a few connections. You can skip the connections. So, you can add the dropout at an hidden layer, you can add the dropout even at an input layer. So, you can specify the dropout anywhere between 10 to 50%, not more than this, because more than 50% if you drop, I think the performance of the model drastically reduces. So, this is all what we have seen in this particular lecture. So, we will be stopping here and then immediately we will be moving now to the hands-on using Google Colab. I will stop the slide presentation and then I will present you the Google Colab. So, whatever we have seen in the theory session so far, let us see that in the practical. We are seeing an multi-layer perceptron one problem statement, and what we are seeing here is the classification. We are considering a classification data set. Okay, what is the first step that you will do? We are running this program in Google Colab. You can even do it offline also. You can run the program even in Jupyter Notebook, because the data set that the size of the data set Jupyter Notebook also works very well. Okay, so in Google Colab, the first step is you have to import the necessary packages that are required for you to run your program. So, as and when we see the cells, we see the line of a code, I will be telling you the packages. So, for now we are importing pandas. Pandas is required in order to read for your data set. Now, what kind of data that we have considered? We have considered the data in the CSV format. So, we have, because the data is in the CSV format, the function that we are using here is read underscore CSV. Suppose when you are solving a problem, if you come across an data which is stored in .xlsx format, which is an Excel format, then the data set that the function that you will be using here is read underscore Excel. You will use read underscore Excel, because it is CSV file. We are using read underscore CSV. Read underscore CSV is a part of pandas. So, pd dot read underscore CSV. Now, whatever the data that you have read, it is assigned to a variable. Since it is the data set that we have considered here is predicting whether a given instance is cancerous or non-cancerous, and here this is the data set which is focusing on ovarian cancer. Therefore, the variable that we have used here is cancer. So, we want to visualize how the data set looks like. So, we are printing the first 5 rows of data, that is dot head. Now, if you see here, if you look into the last column, here we have data, because it is just a head, we are able to see only 5. Otherwise, when we look into the entire data set, we will be able to see that it is a binary classification problem. Okay. So, with this, what are we understanding? It is a binary classification. So, once you know that it is binary classification, try to recall what all that you have learnt. If it is a binary classification, how many neurons that will place at an output layer? So, you can note down the number of layers that you place at an output layer will be 1. Then what is an activation function that you will be using for that output layer? For that one neuron, we will be using a sigmoid activation function. Good. Next, what is an optimizer? There is no restriction on an optimizer. What is the loss function that we are going to use here? Because we are dealing in binary classification, the loss function is binary cross entropy. Next, so that is all with respect to an output. Now, hidden layer, there is no restriction, as we have seen. Now, before we go into building, look into number of features. So, when we print dot head, we may not be able to see all the features that are present. So, go to use the function called shape. Shape because your entire data is stored in a variable cancer. So, give cancer dot shape, that will give you what is the size of your data set. So, the size of your data is, we have 349 rows and we have 50 columns. When I say 50 columns, even this includes the last label also. So, so how many number of features are there? There are only 49 features, because that 50th feature is our label. So, number of features what we have are 49. So, with this, what is that next thing that you should remember? Okay, if there are 49, when we are building a model, our input underscore dimension should be 49. So, this is all you need to have in your mind before we start building a model. So, before we even proceed with this, there are a few more things that you need to do. So, what is that we will now do? We will separate the entire X and we will separate the label. So, leaving the label, all the features are considered or given to a variable X, and the label which is a type is given to a variable called Y. So, how is that we will do? We want all the features, but we do not want that Y, we do not want the last column and the name of that column is a type. So, what is that we should do? We should call the function drop. What this drop function will do? It will drop. So, you need to specify what it has to drop. So, what we want it to drop? We want we want type to be dropped. Now, this drop should happen on a column, not on the row, column. Therefore, you need to specify axis is equal to 1. When you specify axis is equal to 1, it is going to drop the column. Which column it has to drop? The column by name type. So, this entire, if you drop this, what is left out to you? You will be left out with only the features up to AFP to UA, up to this is what is your X. That entire is assigned to X. And what is Y? Y is only your label. So, how do you specify this? Only label, that is a type, is given to Y. So, I hope this is clear to you. What is that we have done? We have separated all the features and then we have separated the label. Next, there is one pre-processing that we have to do, not once again a compulsory pre-processing step, but when we look into this particular data set, we see that there are some values which are very less. The values are very small. If you see 0.01, the value of this feature is very small. But if you look into some other, if you see this UA, the values are very high. So, in order to avoid the biasing to a model, model should not think, okay, UA value is very high, that means I need to give more importance to this. This BA is this value is very small, so that means maybe this feature is not that important. So, we should not give any sort of a biasing to the model. So, what we are going to do, all the values which are here in this data set, we are going to change the values. We are going to scale down to one particular range. What is the range that we are going to? We are going to bring down the values between 0 and 1. Whatever the values. Now, we have a value 0.01 and here we have a value 73.9, we have a value 396.4. Rather than having a values like this, all these values will be scaled down to one range, that is 0 to 1. So, that is done by using it is a pre-processing step, and we have a function which is which does this, and the function here is min max scalar. What is a min max scalar? What is the formula used for min max scalar? The formula used here is x minus x min whole divided by x max minus x min. For example, if you take this, here you may not be able to visualize, I will show you with this example only. You correlate it to the value between 0 and 1. Suppose in this entire column, it just not take only phi, it will take the entire feature. Now, if you take x as, if you take this feature AFP, in this entire column, what is the minimum value that we have? For example, if that minimum value is 1.50, if that minimum value is this, and if the maximum value is 34.24. So, what is the minimum value? 1.50. What is the maximum value? 34.25. So, now come back and then substitute the values in this. What is x? X is which value you want to change? I want to change this 3.58. This 3.58 minus what is the minimum value? Minimum value is 1.50 divided by, you have max minus min. So, when you substitute in this, you will get one value. That value is what you are going to replace this 3.58 to its equivalent value. That value will be between 0 to 1. Similar way, the next number, x value will be 34.24 minus the minimum value 1.50 whole divided by 34 maximum value. What is maximum value? If that maximum value is 34, max minus minimum value. So, you are going to replace each of these values. That is how this min max scalar works. So, min max scalar is mainly used to scale down our values, scale down the values which are there in the data set. Why is that we have to do this? We have to do this because we do not want to give any sort of an impression to the model that some values are very large. So, maybe this feature is important, some values are very less, that means this feature is less important. No, in order to avoid any such sort of an biasing, we are bringing down everything to one particular. Okay. So, you are calling this min max scalar and it is assigned to this particular variable, and using this you are going to transform all the values which are stored in this x. What is stored in this x? All the feature values complete in your data set, the entire feature values are stored in this x. So, the same step should be repeated for all the columns and all the values which are stored in that particular column. So, this is what the changed values are stored in x underscore scale, the updated values are stored in x underscore scale, and when you print it, this is what you are going to see. So, here all the values are scaled down between 0 and 1. So, I hope this step is clear to you. So, this is mainly used to scale down the values. Then is it the only method that we have? Is the min max scalar is the only method? Answer is no. We have a few other methods also. There is one more which is shown here. We can even use a standard scalar. Standard scalar is one more technique which is used to scale down the values. So how is that you will use? Call the standard scalar function, assign it to one variable, and then you transform all the values which are stored in that particular. So why is that we are using a fit underscore transform? What is the meaning of a fit underscore transform? Let's go back to min max scalar only. In min max scalar, how does it works? The first step is it has to calculate all the minimum values, the minimum value in that entire data set and entire feature, and it has to calculate the maximum value. So what does the fit does? Fit is going to calculate the minimum value and it is going to calculate the maximum value. Then once it calculates minimum and the maximum value, using that minimum and the maximum values, you are going to transform all the values. That means you are going to apply to this particular formula, and then you are going to calculate, you are going to get the scaled values. So this is what is a fit underscore transform. Fine, let us proceed. So what is that we have done so far? We have read the data set, we have split the data, we have separated the features and then the labels, we have separated as independent features and dependent features, and then we have done a pre-processing where we have scaled down the values between 0 and 1, or or we can use some other method for scaling down the values, that is a standard scalar. Then what we are doing next, the next what we are doing here is we are going to split the data. How is that we are going to split the data? When you take your data set, you will have X test, Y test, you will have X train and Y train. So we want to split the data into this training and testing. So when you are splitting this, how is that, how is that you will do? You will import train test split from where? From sklearn. Sklearn package, you will import train test split. Now to this train test split, what all you will pass? You will pass X scale. Now we will not pass X because X has some values more, some values less. In order to avoid this, we have already scaled the values, right? So which method you have used to scale down the values? We had used min max scalar. So all your values, scaled values are stored in a variable X underscore scale. So we will pass X underscore scale for splitting, but not X. I hope this point is clear to you. Then along with that we will also pass Y. Y we have not disturbed. Then how much percentage you want to give it for training and how much percentage you want to keep it for testing. So here for a train test split, we only pass the parameter test underscore size. When we pass this as 20%, automatically the training will be 80%. So when a test size is 20, training will be 80%. Now here one more point you need to focus, whether always we should go for 80-20. Answer is no. You can even have test size as 30%, 0.30, then your training will be 70%, then you can have your test as 0.4, then your training will be 60%. So you can have a range ratio between 60-40, 70-30, we can have 80-20, 90-10, then we can have 75-25. You can decide your train test ratio like this. Avoid having a 50-50%. Don't give a test size as a 50%. No, that is not a good ratio. Try having a 60-40 size. Then we are specifying a random underscore state. Why is that we require this particular variable? What is the role of this? Now I want my data data to be results to be reproducible. What does it mean? Rather than every time when you run the code you are getting a different result. In order to avoid that, each time when I am training, I do not want to take different values. So then you will write random underscore state as true, or you will pass some value, so that you will not get different results each time when you run the code. Yeah, so I hope this is clear to you. Now by executing this, you are going to get the values for X train. You are going to have your entire data set as X train, Y train, X test and Y test. So all that is been. Here is where you are going to build your neural network. So how is that you are building your neural network? You are using a Keras. So you are importing a Keras. Keras is part of TensorFlow. So import Keras from TensorFlow. Now what kind of model we are building? We are building a sequential model. We will have an input, then we have an hidden layers, then we have an output layer. So it is a sequential model that you are building. So import sequential. From where are we importing this? From Keras models. Then it is a dense, fully connected neural network. So import dense. So dense, we are dealing with respect to layers, right? Because from one layer to another layer you are establishing the connection. Therefore Keras dot layers. Okay. Now what kind of problem statement we have considered? We have considered binary. On what basis we are saying it is binary? We see the last label, we have a binary one. Okay. So because it is binary, how many neurons should be there at an output layer? We should have only one neuron. Then what is an activation function we should be using? We will be using a sigmoid activation function. Good. Next, let's come to a hidden layer. How many number of hidden layers? Is there any restriction to this? Answer is no. You can have any number of hidden layers. So here how many hidden layers that we have considered? We have considered 2 hidden layers. So the first hidden layer has 32 neurons, the second hidden layer has 32 neurons. So we have 2 hidden layers, 32 and 32. Next, for the first hidden layer, what is that we are passing for the first hidden layer? We pass the input. So how many number of features are there in the input? We have 49 features, right? We have 49 features. If you go back to your data set, in the shape we have seen, we have totally 50, but in 50 we have, it is 49 plus 1. So we have 49 features. So for the first hidden layer, I want you to imagine this neural network diagram. So you will have 49 neurons. If you visualize this, you will have 49. Then you will have 2 hidden layers with 32 neurons, and you will have 1 neuron at an output layer. So I want you to have this diagram in your mind. Now how is that you are going to code it? So for the first hidden layer, what is the input that you are passing? Is it not 49 features that you are passing as an input to the first hidden layer? Therefore you see, for the first hidden layer you are passing an input dimension as 49. Now few will also write it as input underscore shape. Instead of writing, we can even write in this way. We can have even input underscore shape, and when we write input underscore shape, expects the value in a tuple. So we will be writing 49. So we can even write in this way rather than passing to input underscore dimension. So easy is go for input underscore dimension, because you know that there are 49 features, so you will be passing 49. There is no difference between input underscore dimension and input underscore shape. It is just a change in the representation. Okay. So I hope this is clear to you, because it is an hidden layer that we are talking about. The activation function that we are using is a ReLU activation function. So this is the model that we are building. Once we build the model, what is the next step? You have to compile your model. So how is that you will compile the model? So we use a function called compile. For compile, what all we require, once you build a model, when we execute it, what is that you are going to get? You are going to get the loss function, you are going to get the loss, you are going to calculate the loss, you are going to calculate the performance of your model, and then your aim is to reduce the loss. So, that means you have to pass 3 parameters to your compile. What are the 3 parameters? You will pass the optimizer, you will pass the loss value, and you will also pass the metric. Because it is a binary classification, what is the loss function that we are using? Binary cross entropy loss. We are passing binary cross as a loss. Then because it is a classification problem, what is the metric that we are using? Accuracy, which we have already seen. And here the optimizer that we have used is Adam optimizer. Is it compulsory that we should use Adam optimizer only? The answer is no, because based on your problem statement, based on your data set, based on what kind of data that you are using, what is the size of your data. So, based on so many of these parameters, you can keep changing this optimizer and you can run the code. Next, you are training the model. What is the function used to train the model? We use the function called fit. For this training, what all that you will pass? You will pass X train as well as Y train, because during a training you should pass both features as well as labels, right? You will pass both the dependent and independent. So, X train and Y train, you are passing it to the function fit. Then for how many epochs that you want to run? You want to run this for 15 epochs. So, yeah, once again, just for demonstration, I have used the number 15, but when you are dealing, when you are doing a project, when you are working on a larger data set, change this to a larger number, so that higher the good, you will be getting a good training, you are training for a good period of time. Next, there is something called as batch underscore size. Why is that we are why we are writing batch underscore size is, now rather than taking the entire data for training, rather than taking all the samples, I am learning in batches. So, I will first take 32 samples and I will learn. I will take the next 32 samples, I learn. So, batch size we are specifying. So, you are training the model in batches rather than training by passing the entire. That is what is batch underscore size. You are specifying a number here. Okay. So, I hope this is clear to you. Once you train your model, once you train, fit is used to train your model, you can able to see that for every epoch how the model is learning, what is the loss that the model has obtained, what is the accuracy that the model has got. So, by end of these epochs, you will be whatever the accuracy that you are getting, whatever the loss that you are getting is the training accuracy and training loss. Once you feel that the loss is considerably reduced, then you can go for evaluating, you can go for testing your model, rather than in case if the training loss itself is very high, then there is no point in predicting, you are passing new samples for prediction. So, go back and then change the model, see that increase the epochs. Probably maybe this particular optimizer is not functioning well or suiting well for this data set, for the data set that you have chosen. So, change, and then always once the training performance is good, both in terms of accuracy and then the loss, then only go for evaluating your model. How is that you will evaluate? So, the model that you have built sequential is entirely stored in a variable called model. To this model you have added the first hidden layer, to this model you have added the second hidden layer, to this model you have added the third hidden layer, third layer, not hidden layer, the third layer, which is the output layer. So, now this model you have compiled. So, model dot compile, this model you have trained. So, model dot fit. Now, when you are predicting, you will obviously predict by using the model that you have built, right, which is there in the variable model. So, model dot predict, model dot predict. Now when you are predicting, what is that you will pass to this? Obviously the unseen data, right? What is unseen data? During a training, what is that model has seen? During a training, model has seen X train and Y train. Now what is that the model has not seen? It is X test. So the data which is stored in your X test, the features or the samples instances which are stored in X test. So you are passing that to your predict function. So all the values that you are passing it to predict, the model y underscore predict is where you are going to get the result of the prediction made by the model. Then whatever you are going to get the values in y underscore predict, you will be seeing that the values will be between 0 and 1. Why the values will be between 0 and 1? Because what is the activation function that we have used? Sigmoid. What is the formula for sigmoid? It is 1 divided by 1 plus e to the power of minus x. This is a sigmoid value. Sigmoid will always give the values between 0 and 1. So now what if you look into the diagram of sigmoid curve, so sigmoid curve will have at point 5 it is going to have its curve. So so any value which is greater than 0.5, because ultimately our aim is it is a binary classification. It has to predict either the class 0 or it has to predict the class 1. But what does this y underscore predict will give us? Y underscore predict will have a value between 0 and 1. So what is that our ultimate aim? Ultimate aim is you should get the answer in terms of zeros and ones. So what we will do, any value which is greater than 0.5, we will convert that to 1, and the value less than 0.5, the value will be, the class will be 0. And then we are converting the value into integer, and finally you are getting your y predict answer. So here just for a visualization to see how y predict and y test, you are placing these two side by side. Therefore we are using this particular column underscore stack. Column, it is a column, and the stack is placing one sequentially, one after the other, so that you can able to visualize this. I hope this is clear to you. So whatever the model that you have built for this ADAM optimizer, whatever the 2 layers with the 32 neurons, the accuracy what we are getting here is around 82%. This is the accuracy that we have got. So if this is not, if you feel the accuracy has to be improved further, then what is that we will do? We will go back and then fine tune all the parameters. What are the parameters that we have? What are the parameters that you can change in order to improve? Probably you can change the optimizer and see how it is performing. Probably you can change the epochs, train for more number of epochs. Probably reduce the batch size and then see how. Then try increasing. See, there is nothing that you can do with 49 and this one. Let us talk about the dropout, but otherwise for this given model, for whatever the model that we have built, if you want to do certain changes, probably we can add more number of hidden layers, maybe add more number of neurons, and then see how the model is performing. So this is how we are going to fine tune the parameters and see how the performance of the model is varying. So one more way to improve the accuracy is you can go for dropouts. As we have seen in the theory session also, there is a dropout concept. You can apply dropout at an hidden layer. We can apply dropout even at an input layer. So whatever the code that you are seeing here is a dropout which is added only to the hidden layer. Why only to the hidden layer? There is no particular reason. We are trying out to we are just trying out where the dropout is added to the hidden layers only. So, you can try adding the dropout to the input layer. So, what is being shown here is adding the dropout at the hidden layer. So, we are specifying the first hidden layer, and then we are writing the 20% of dropout. Then we have added the second hidden layer, and then we are adding the dropout at the second. We are adding the 20% dropout at both the hidden layers. And then this is the only change that we have bought, and once again the optimizers are same as the previous. Number of epochs and the batch size is the same. Let us see how the model performance is varying. Previously we have got 82.87% accuracy. By adding the dropout, we have kept everything as the same optimizer, same epochs, same batch size, same number of neurons. Only change here is we have introduced the concept called dropout, and then we could see that there is a slight improvement in the test accuracy, that is we are getting 84.28. So, once again here, not necessarily that each time we add a dropout the performance will improve, not necessarily. So, once again maybe for some data sets by adding the dropout the accuracy will improve, for some the dropout will not have any impact. So, it is once again you have to try it out and then see how it is having an impact. For the interest of the participants here, let us try to understand what exactly is this. We have something here 33, 8, 3 and 26. What exactly is this? So, this is something a fundamental concept when you talk about machine learning, deep learning. This is called a confusion matrix. So, in the confusion matrix, how did we get these numbers? Is it not that we got these numbers by considering the two data? What are those two data? We have considered the predicted value y predict, and we have also considered y test. We have a ground truth and we have a predicted value. So, using these two, we have y predict and then y test. Using these two values, we have calculated your confusion matrix. Now, that means we have an actual values and we have predicted values. Look at this, we have an actual values and we have a predicted values. Okay. Then in this number 33, 8, 3 and 26, how is that we are going to read? We are going to read it as true positive, false positive, false negative and true negative. What is the meaning of each of these is? Suppose actual answer is 1, the ground truth is 1, model also has predicted it as 1. So, it means it is a correct prediction, right? Model has predicted correctly. The first T, how is that we have to read the first T? What is the meaning of first T is? Model predicted the value. What model predicted is exactly matching with the ground truth. So, it means model predicted correctly. So, it is true. If model has predicted correctly, then what is that model has predicted? Model has predicted it as a positive. Okay. Let us understand this, false negative, false positive. Now, actual was supposed to be 0, but by mistakenly model has predicted it as 1. So, actual was 0, model has predicted it as 1. So, definitely what model has predicted is wrong. It is a wrong prediction made by the model. Therefore, you are reading this first as F. F is model has predicted wrongly. Okay, if model has predicted it as wrongly, what is that the model has predicted? Model has predicted it as positive, but actually it was supposed to be negative, but model has predicted it as positive. That is what is false positive. Similar way, on similar lines, let us understand what is a false negative. So, actual was supposed to be 1, but model has predicted it as 0. So, actual was supposed to be 1, but model has predicted it as 0. So, it means it is a wrong prediction. Prediction made by the model is wrong, because something it was supposed to be 1, but it has predicted it as 0. So, it is a wrong prediction. Because it is a wrong prediction, we are calling it as false. Okay. If it is a wrong prediction made by the model, what is the prediction model has made? The model has predicted it as 0, Actually it was supposed to be 1, but model has predicted it as 0. Therefore, it is false negative, true negative. Actual was supposed to be 0, model also predicted is 0. So, 0 and 0. So, model has predicted it right. So, therefore, it is true. If it is true, what is that model has predicted? Model has predicted it as 0, negative. So, true negative. So, what is always the aim should be the diagonal values, this 33 and 26, this diagonal, the principal diagonal values or the forward diagonal values, if the values are more, it is good, but the secondary diagonal, the false positive and the false negative, these values should be as less as possible. If it is 0, it is very good, but otherwise it should be as low as possible. Otherwise, it is not correct, right? Actual was 0, but model has predicted it as positive. In this case, if you take in medical applications, the person is not having a cancer. If you take this particular data set, ovarian cancer only, the person is not having cancer, negative, but model is predicted it as positive. So, which is very dangerous, it is not correct. So, false positives should be very less. Then look at false negative. Actual was positive, but model has wrongly predicted as there is no cancer. So, in either of a case it is very wrong. So, the interpretation of confusion matrix is very important. Always ensure these error 1 and error 2 should be very less, as small as possible. So, we have a type 1 error and a type 2 error. This we call it as a type 1 error and this we call it as type 2 error. So, this is what is all about the multi-layer perceptron, artificial neural network, ANN implementation. So, I want the audience or the participants or the learners who is listening to this, when you are dealing with, when you are taking a project, look at the data set. So, what are the steps that you will take? Look at your data set, understand whether it is an binary classification problem or whether it is a regression problem. Okay, let us take, suppose you are dealing with the regression problem. So, your data set, what you have taken is a regression. So, what are changes instead of type 0, 0, 0, 1, instead of binary classification, let us assume you have some numbers here. So, it is a regression data set. If it is a regression data set, there is absolutely no change with respect to this. There is no change in pre-processing, there is no change in train test split, it does not have any impact. Change comes here. So, if it is a regression problem, you will still go with one neuron, and the activation function you can go for linear activation function. Then when it is a loss function, use mean square error loss, and the metric what you will use is MSE metric. Okay, or you can use mean absolute error MAE, and you can use metric as MAE or MSE. These are the changes. Absolutely there is no change with respect to optimizer, because irrespective of anything, optimizer work is when it is coming back in the during the back propagation, it has to update the weights. So, optimizers will remain the same, whatever those 7 plus 3 optimizers that we have seen in the theory session, you can use any of those optimizers. This is the change that you are going to do it. So, try out with a different number of neurons, different number of layers, and see how the model is performing. So, this is how we are going to build a model. There are other techniques in pre-processing, like if there are many outliers, so you can remove the outliers, you can deal with outliers, that is one. Then here already we have the output label in terms of zeros and ones. Instead of zeros and ones, if we had cancer and non-cancerous, then we have to use either label encoding or one hot encoding. All that we will do in the pre-processing stages only. So, I hope ANN is clear to you. This is how you will build the model. So, with this we are stopping this particular session. In the coming session we will be seeing CNN, convolutional neural network. First we will see the basics that are required, and then we will be moving to the hands on. Thank you.